Cruising is unlike anything else. Our 3 cruise lines travel to every corner of the globe, providing exceptional guest experiences to see, understand, and appreciate the world from a whole new perspective. It's at the heart of what we do. The future of our business is dependent on the beauty and wonder of our planet.
Our Sail and Sustain program is our commitment to cruising responsibly and protecting the oceans we love. We focus on making a real difference both at sea and on shore, because cruising depends on healthy oceans and thriving communities. It's how NCLH shows guests, employees, and investors that we are serious about reducing our footprint, creating value for our investors, meeting global sustainability goals, and staying ahead of regulations.
So welcome. Thank you all for coming, both those here in person and those online. I would like to thank our sponsors, our presenting sponsor, Norwegian Cruise Lines. This is the second year they've done that, and we are very grateful for their support. Our supporting sponsors include the Shepherd Broad Foundation, Bill Galway, KB Life Enhancement Forum, the Key Biscayne Community Foundation, Joan McCann Family Foundation, Nicole and Myron Wang, and Southern Glaciers Wine and Spirits. So thank you to our sponsors. Continuing on in my dean duties, they put it in here. I didn't write this. If you have enjoyed joining us for Sea Secrets, learning about our programs, and hearing from our presenters, I welcome you to join us in becoming a supporter if you're not already one, and a hearty thank you to everyone who does support Rosenstiel. So genuine. A personal priority of mine is creating more opportunities for our students to do experiential learning, to get their feet wet and their hands dirty, and that does take resources. And so if you're interested in helping us grow our experiential learning, please reach out to Jennifer Dillon. Jennifer, please stand up and wave. Jennifer is our development officer, so if you want to talk to Jennifer, learn more about these opportunities after the event, please feel free to do so. Okay, so Marybeth, so now we're starting to cross into the Bend territory. We're getting close. So, but first, Marybeth gave me what she wanted me to say about her, right? Fair enough, I should say that. So I'm gonna give Marybeth's bio introduction, and then I'm gonna give you the real introduction, okay? So Marybeth is an assistant professor. She's jointly appointed at the Rosenstiel School and at the Institute for Data Science and Computing here at the University of Miami. So we have 6 of these positions. We're really excited about these positions, these joint positions, and you know, you're gonna see Marybeth's work is really leveraging that institute. So she's really bringing data science, AI into the Rosenstiel School. And we have 6 of these folks here that are really bringing that new expertise to the discipline-specific work we do here. So we're really excited about these positions, and so is iDisk. I'm the deputy director over there too. I wear lots of hats, and so I can tell you authoritatively that iDisk is very excited about this. Marybeth is a member of the U.S. CLIVAR Predictability, Predictions, and Applications Interface Panel and the Working Group on Climate Data and Predictions for Coastal Solutions. She is also the co-chair of the American Meteorological Society Accessibility Committee. She received her Ph.D. in Atmospheric Sciences in 2021 from the University of Miami Rosenstiel. Hence, we're going to get to the Bend part of this story. Okay? She also has a bachelor's in mathematics from Georgetown University in 2014. And I think Marybeth skipped a couple things. You did, it was a teacher thing, or was it, what was the thing you did in the Far East? Yeah, second grade teacher. What country were you in? Micronesia. So when first Marybeth interviewed with me, you know, when she came back from that, you know, there was some time in between. She wanted to go on to graduate school. First button she pushed to mind was the mathematician. I'm originally trained as a mathematician. Said, oh, this kid's going to be good. I was really excited. This kid's going to be good. And then she did this work in Micronesia teaching second grade. I said, not only that, she's got a great heart. So how can I go wrong, right? So now I'm going to start to drift into the Ben mode, Marybeth. So if you hadn't guessed, Marybeth was my student, my PhD student. So when Marybeth actually started being a PhD student, she knew nothing. It was a blank slate. She knew nothing about climate. She impressed me so much of how little she knew about climate. I thought it was amazing that someone would decide to do climate and just knew nothing. But Marybeth really, really did persevere. At one point I think I told her, you don't appreciate, because you don't have the long view that I have of how you've evolved and matured as a scientist. It's the greatest thing as a PhD advisor to watch a student come in and believe everything I tell her, right? Everything I tell her is gospel, and then by the time we're done, she'll tell me something and I'll pop off and she'll say, you know what? I don't think you know what you're talking about. And I will say, perfect, it's time to graduate. So besides that, Marybeth was such a joy to have as a student. She started a blog site, a website called Seasoned Chaos. If you ever have an opportunity to check it out, it's a fantastic, easily accessible discussion of climate variability and climate topics, including change, but all of these things that you hear about this meeting, but in a really accessible way. Talks about the meridional overturning circulation, the North Atlantic oscillation, all these acronyms that we have, but they really bring it down to a very accessible level and really provides a nice background. And this was a project that she and her others, I had a big group in those days, I still have big, but a large group, they put together without consulting me. They did it all on their own. I had nothing to do with it, but I took full credit for it, believe me, all the time. So it's really my legacy when I'm done is going to be what happens to my students. So I already know Marybeth is fulfilling her obligation to make me famous. So Marybeth, please, I'm done embarrassing you for a little while. Please come up and tell us everything we need to know.
Hi, everybody. Thank you very much for the introduction. I think it should show you that Ben took me knowing I didn't know anything, so maybe he's a little off his rocker, but I'm so grateful. I loved being a student here so much. It was such an easy choice to come back, so thank you. I also want to thank the Sea Secrets organizers, Deanna Udell, and all of the organizers who have gone into making this happen and behind the scenes. So thank you all. And of course, the sponsors as well. I really appreciate everything going on to make this happen, and you all for being here. Let me get this. Today I'm going to be talking about AI in climate prediction, and I see myself as a climate scientist who uses machine learning and not the other way around. And so I'll be talking about how we use machine learning and these AI tools, but to answer climate science problems with the human component an integral part to this. And so to make predictions about any system, we have to understand how it works. And so I love this snapshot of the globe here because it really gives this bird's eye view. We heard recently it's 1 billion butterflies flapping its wings to get to this moment in time right here. But we can also see the immense complexity that goes into this image here. And this is just one moment in time. And so beginning to think about the complexity of this system to actually make predictions about it, we have to break it down into simpler terms. And so this is taken from the blog that Ben had mentioned here, which is how me and the Seasoned Chaos team like to think about this is the climate system as this weather pattern pie, where we have all these slices broken up into different time components, space components, that all feed together to lead to that picture, and then to actually make predictions about the future. And so one slice where I really spend a lot of my time thinking is right here in this sub-seasonal time frame. The sub-seasonal is considered this bridge between weather and climate, falling anywhere from around 2 weeks to 3 months. But what we can see is that we have notably low forecast skill on this time. And so we can't expect to make perfect predictions all the time due to this complexity. And so what we look for are windows into this time period where we have higher skill. And so we look to identify predictable states of the climate system that lead to not only higher skill on this time frame, but also higher confidence. This is what we call forecasts of opportunity. And so a driving research question in my group is, what are the sources of predictability that ultimately lead to these forecast windows of opportunity? And so this has been studied for decades here, and so it's been widely studied, these different climate modes of variability, these different slices of pie that can lead to these forecasts of opportunity. And so, along with Ben, I have been studying these now for about a decade, and still looking at this picture makes me go like this. It is so difficult to try and piece apart these things. And this is where machine learning really comes into play. And so as a climate scientist, we have a toolbox of all different analysis tools. And machine learning is, in fact, a tool in this toolbox. And so here we take this noisy climate system, and we can use neural networks, machine learning tools, to actually extract noise from the noisy climate system. And so we leverage machine learning for two important tasks here for these forecasts of opportunity. The first one is quantifying accuracy. So this is a simple image here of a neural network where you have some input, you feed it through these hidden layers, this black box, to make some sort of prediction. We compare this against the truth, we figure out what went wrong, we go back into these hidden layers, we update it, and then we make a new prediction. This is an iterative process, what we call training a machine learning model. Now, things like ChatGPT, your Tesla, these types of things use neural networks, but at the scale of billions. But what I want to emphasize here is that they all come down to this structure. Machine learning is not magic. It is just a lot of calculus. And no one wants to be doing that all in their head. We use computers to do it. The next really important part of machine learning is that we can leverage it to quantify confidence in our predictions. And so a pretty classic machine learning task is you give it an image, say this image here, and we say predict what this number is. And so it outputs these seemingly nonsensical numbers, but then we can convert these into probabilities. And so here we can see we have three choices. It's either 5, 6, or 7. There's a 67% chance that it's a 7, so it predicts that. But then we can also look and see that there's about a 1/3 chance that it's a 5. There's only 3 choices, so kind of random chance. But then we also see there's basically 0 chance of it being a 6. So we can get confidence in the probability of a predicted output. Taking this one step further for forecasting, we can also get better uncertainty. And so we can use neural network predictions to capture spread in predictions, which is really useful for forecasting and communicating our forecasts. And so, as a climate scientist, with the tools that we use, it's important to ask the next question of how can we trust these black box AI models? And this is at the heart of what we are asking here about any tools that we're using. And this is where explainable AI comes into play. So explainable AI is when we go back into this network and we actually find what pieces of those hidden layers actually contributed to the prediction that was made. And so in this way, we can utilize the network itself to better understand the climate system. So let's see how this works. So explainable AI is a suite of techniques that explains the decision-making strategy of a neural network. So here's an example. Now we have this picture of a rooster. We feed it through the black box and it says it's a rooster. Yay! But why did it say that it was a rooster? And so we go back into the network and we can create these heat maps that show what in the picture actually contributed to that prediction. So here we can see it's the crown, the wattles, which is probably what we all subconsciously used to know that this was a rooster. And so this is how we build trust in our models. Whoops. So now let's look at another image. Now we have the cat, and now we can see that it's the pointy ears, the nose, and the whiskers. Again, what we as humans are using to determine that this is a cat, building trust in the model. This last image here is an image of a horse, but what the model was showing, what the XAI was showing is most important, is this bottom left corner. And that seems weird because it's dirt. So then the scientists went into this suite of images and found that all of the images that were used to train this model were actually from the same photographer who watermarked their images, and that was watermarked right here on the bottom left of this image. And so even though it's hard to see by eye, we can also use these techniques to figure out, arguably as importantly, when a prediction was made correctly but for the wrong reason. Something else I really like about this example is that it's from a dentistry journal. I don't know anything about dentistry, but it shows the breadth of these tools and the utilization that we are taking from the computer science community who are developing these techniques to be used across so many different fields. And so explainable AI is seen as a game changer in climate science because not only can we fine-tune, optimize, do things cheaper and faster, but we can build trust in these black box models. Are they making the right decisions for the right reasons? And ultimately, with that, we can then learn new science. And so I want to take some time to go over how we are using these tools to enhance climate prediction in my research group. We are a team of a postdoc, Ph.D. student, and an undergrad researcher utilizing these different tools that I'll go into a bit more. So the first is building a real-time forecasting tool. This is a project funded by the NOAA Weather Program Office, and it's a collaborative effort with Dr. Emily Becker, who's the deputy director at the Cooperative Institute across the street, as well as the NOAA Climate Prediction Center, Colorado State, a big team here. Here is the precipitation outlook that was issued on Friday from the Climate Prediction Center. So we can see that there's some regions of the country that have above chances of normal, below chances of normal of rain. But we also see that large swaths of the country have equal chances, essentially no skill. This is just one forecast, but precipitation is notably hard to forecast, especially on this subseasonal timescale. And so if you remember these windows of opportunity that we're looking for here, we are building a real-time forecasting tool to figure out when, where, and why a forecast in this realm could be considered a forecast of opportunity. And so how we do this is we ingest states of the climate system, so maps of different climate variables, and we can build a neural network to predict, is it going to be rainy or dry in 3 to 4 weeks, say along the west coast of the United States. And so we do the training process, the testing process, and we can compute our accuracy and our confidence. And so when we go through, we can look at our accuracy here on the y-axis as a function of confidence. And so our model, as we go from left to right here, is getting more confident. And we see that as the model gets more confident, it also gets more accurate. And so what that means is that there are predictable states of the climate system that the neural network has learned to make these accurate and confident forecasts. So, yay. That seems great. But what did the network learn to actually get these confident and accurate forecasts? And so we use XAI, we open our black box, and now these purple regions are showing which spots in the globe actually contributed to these more accurate and more confident forecasts. And so we can see here, we have the maritime continent region, the tropical western Pacific Ocean, and these are the regions that contributed to this forecast of opportunity. And so work that I did once a long time ago with Ben, and also tons of people have been looking at these types of things with lots of different techniques to try to understand these large-scale climate modes, slices of pie, that are contributing to forecasts of opportunity. And so we had found a few years before that it was those same regions that led to predictable rainfall along the West Coast. And so again, this is getting back to building trust. But now we did this in a brand new model, much faster, and we can actually understand how we were able to produce these forecasts of opportunity, something that we weren't able to do before. I had also mentioned quantifying uncertainty. And so we can, instead of asking, is it going to be rainy or dry in 3 to 4 weeks, we can actually get a spread of scenarios or a range of scenarios about what could happen. And now we can start to ask questions like, what's the probability of exceeding some threshold? We can think about extreme events. These are really important metrics for decision makers, water managers. Think about if we are going to exceed some threshold and dams need to be lowered, pumps need to be activated. And these thresholds can change based on region, based on season, based on event. Something that I really enjoy about this project is this is where predictability is meeting prediction. Meaning that what we are learning about the climate system is actually being utilized to improve forecasts in real time. So now we're at the Rosenstiel School after all, so we're going to be moving from the atmosphere and into the ocean. And so we are also building a prediction system for heat stress for coral reefs. This is another NOAA-funded project that's also collaborative with the Cooperative Institute's NOAA Coral Reef Program. And so it likely comes as no surprise that the warming temperatures off of our coast are leading to coral decline. And this became extremely evident during the marine heat wave of 2023, when the reefs off of our coast saw 3 times the heat stress that had been previously measured. And this led to a race by conservation managers to go out and try to preserve some of the genetic biodiversity of the coral reefs that were threatened from this heat wave. And so there's a suite of tools out there working to predict these heat stress events that provide a huge resource to the community. But this event also motivated us to build a localized and purely data-driven machine learning-based model to predict this heat stress at the reef scale. And so we took 3 reef sites here, Molasses, Sombrero, and Sand Key Reef, along the Florida Reef Tract. And we took data from both the NOAA Coral Reef Watch and the NOAA Physical Sciences Lab to get information about the localized heat stress at the reef, as well as global predictors, regional and global predictors. We built a boosted random forest classifier, which is a series of thousands of decision trees. So you can think of this as thousands of yes or no questions. And we predicted if and when heat stress will occur. So will heat stress occur in a season? And if so, will it happen between 0 and 6 weeks from now? And so we specifically focused on this timescale because we wanted it to be an actionable timescale, thinking about what would be a useful time period for these these conservation managers to allocate resources to make preparations if we were to see another heat stress event. And so we can see here, the pink here highlighting our machine learning model, outperforms baseline models at all 3 reef sites. And this is for both if and when heat stress will occur in a season. But you might have figured, where am I going next? What was it about those predictions that led to this skill? And so we use an explainability technique here. This is called SHAP, a XAI technique taken from game theory, where we can rank the predictors in order. And we can do this for each of our lead times. So here I'm showing 2 weeks until a heat stress onset. And we can do this at each reef site, and we can rank the predictors and look at the contribution for every single prediction. And so we're not going to go through all of that. I'm standing between you and the reception, I know that. But what we can see here is that for 2 weeks until onset, it's the heat-related drivers, the localized stress that's the clearest indicator of 2 weeks until onset, pushing it towards that prediction. We see that the second most important is the local circulation, so the local air temperature and the solar flux. And we can also see here that the seasonal timing isn't as important for 2 weeks until onset, but when we look at out to 6 weeks, it's more so the timing and the large-scale predictors that end up being more important. And so we are working with conservation managers to ensure that the most important predictors that we're finding for this heat stress are being locally monitored to be able to better make decisions. And this is a highly collaborative project in terms of the local knowledge, the large-scale information, and we're looking to scale this project up. Can this be moved into real time across more reef sites? And coral reefs are, of course, not the only animal experiencing heat stress in the coastal oceans off of our coast here. And so can we determine and study other heat stress indicators for other vulnerable species? And so just to briefly highlight some other work that we are doing here to look at how we can utilize AI to enhance climate prediction. So again, thinking about that weather pattern pie, we are looking at the full cycle of the climate system, our land, ocean, and atmosphere coupling, and pinpointing the sources of predictability. And using these tools, we can also look at some underexplored sources of predictability. Things like salinity at the top of the ocean that can be a predictor for landfalling rainfall. As well as soil moisture, which can provide feedbacks that also can be good predictors for localized rainfall. We've also been exploring threshold crossing prediction for future climates. And so we can build prediction problems, neural networks, to predict when certain heat thresholds will be crossed at various places around our country, around the globe. And then also what happens when we cross these thresholds. These things can be extended to different sectors. We've been looking a lot at the cattle industry for the middle of the United States. This can be extended to agriculture and crop yields. And we've also been exploring some more sophisticated machine learning techniques like transfer learning, where we can fine-tune machine learning models built solely on climate model data, but then are fine-tuned with observational data to incorporate better predictions of the real world. We've also been using these types of prediction tools to better advance health system resiliency. So this is a project led by Dr. Keelan Ashad-Bishop in our Environmental Science and Policy department here, also collaborative with Dr. Emily Becker and the Data Science Institute, where we're asking what are the environmental factors that can lead to power outages at cancer-providing centers in South Florida? And then can we predict these things with sufficient lead time for proper preparations? And so the last main project that I'll talk about here is this truly groundbreaking advancement in AI in the past few years. And this is purely AI-based digital twins, emulators, Earth system models. They have different names and slightly different nuances. But the idea here is that this is a purely AI-based representation of the climate system. And it looks pretty darn close to the ground truth. And so utilizing this new and very rapid development of these AI-based tools of the climate system to ultimately be able to answer questions that we weren't even able to ask before. And so these emulators use pure AI or a combination of AI and dynamical models to represent the climate system. And so after they're trained, they're able to produce simulations at a fraction of the cost and time that it takes to train our traditional forecast models, our traditional climate models. And so based on this, we can generate thousands of simulations that we wouldn't have been able to do with traditional climate models. And by generating tons and tons of climate data, we're able to do more analysis on extreme events, things like 1 in 1,000, 1 in 1 million year events. As I mentioned, there's been an explosion of development recently with these tools. 2018 is when we can find really the first paper looking at these. And there were about 10 papers between 2018 and 2022. Since 2023, there's been over 50 papers. And I think this is outdated. Literally, as of this morning, I saw a new one come out. They are very complicated. And so this is just a, if you'd believe it, a simplified schematic of one of these climate models. And so while the neural networks that I've been talking about are relatively simple to be able to understand, these are able to emulate the climate system, but then we lose a lot of that explanation that we've been looking for. And so what we are exploring is performing similar research to understand the climate system, but now in these new tools that are representing our climate. And so looking for these sources of predictability from subseasonal out to decadal timescales. Do these sources of predictability align with our previous knowledge, what we find from these climate modes of variability, from our other tools that are highlighting sources of predictability? And then when that trust is built, we can then use these thousands of simulations, the rapid speed, to be able to learn new science, to ask questions that we, again, previously were unable to due purely to computational limitations and data limitations. We've also been exploring looking at future climate scenarios. You can think there's a truly infinite number of scenarios that can be run. And so can we explore this space given these new tools? And so I've been really focused for the majority of this talk on work that we've been doing in my research group here at the Rosenstiel School. But how AI is transforming climate prediction is vast, and it's happening everywhere. And so I just have a few other ways that this field is truly being transformed. And so I was highlighting AI-based climate models, but in the weather space, so up to about 2 weeks, AI forecasting models have already been shown to beat many of our traditional models. And so in operational real time, these models are being used, not replacing, but being used with our traditional forecasting models. We've also seen that AI has been able to help us process, comprehend, and produce vast amounts of data that previously was just simply not possible. We've also seen a rapid advancement in our computing power, able to store and process this data. There's also been a lot of data gaps that have been filled. So regions like the Arctic, the open ocean, places that it's really hard to go out and get observations or even get satellite information. We've been using AI-based methods to actually fill in a lot of these gaps, especially in our data-sparse regions, which can help reduce biases and help improve forecasts everywhere. And then also looking at the very fine scale, another thing that can be quite difficult with our traditional models is looking at this hyper-localized street-level scale. Something that Ben always likes to say is people really care about, when is my street going to flood? When am I going to be impacted? When can I not get to work? That was more of a pre-COVID type thing, though. But these are the questions that people really want answered and what they want to use their weather and climate information for. But getting down to that street level can be quite challenging. And so we've seen advancements in things like fog, urban heat island effects, precise flood risk down to that level where people, decision makers, government officials, and even community members using this information can use to make decisions. Now, I would be remiss if I talked about all of the benefits of AI without talking about the detrimental impacts of AI. And now there's a paradox here where AI has been enhancing climate prediction. That's what I've been yabbing on about for the last 20 minutes. But we've also seen that this development of AI has been having really detrimental environmental impacts. AI centers are incredibly water hungry, energy hungry. A lot of these are being built in rural areas where the impacts of these data centers are truly not known. And so we really are now in the dawn of our next industrial revolution. And being that we're at the beginning of it, we have an opportunity to decide how it unfolds. And so this is a really critical moment now when we get to decide how these tools are being used, how the development unfolds, how we can address these paradoxes. And so I'll leave with these two challenges that I also really see as opportunities here, which is how can we harness the power of AI to innovatively but critically responsibly enhance climate prediction for all people? And how do we mitigate the massive cost of AI development with the environmental factors that drive it? And so, if we are the society, we are the species that can create these tools, then I really do believe that we can come up with the solutions to use these to solve problems and not create them. And that's why we are, that's exactly what this next generation here at the Rosenstiel School is working on. So thank you all very much, and I'm happy to take questions.
Thank you, Marybeth, for that wonderful talk. We have a couple of people running around with microphones. that they need to get from me. Let's turn that on. Any questions for Marybeth over here?
Yeah, that's what I figured.
Hi, being in South Florida, can you talk about how AI would be used in like hurricane tracking and hurricane prediction?
Yeah, certainly. So hurricanes are one of the like benchmarks that these AI-based emulators have been using to determine if they're skillful because of the amount of damage, money, lives lost that can come from hurricanes. The emulators particularly have been really good at forecasting the track of hurricanes. And we've actually, again, seen that they can beat some of our operational models. Where there's been some more struggle is in the intensity of hurricanes. Of course, this is a more challenging problem, but there's been a lot of attention to help use these AI tools to better understand intensity. Now, that's just one way. There's being AI used to fill in gaps in hurricane data, especially because of the cost and danger of actually getting hurricane information. There's AI used to help infill information through the entire structure. Dr. Michael Fisher is one of the other IDISC hires is working on this. And there's plenty of people working on how AI can be used to help with hurricanes. Maybe a next Sea Secrets talk.
Any other questions for Marybeth? Right there. Billy?
Thank you for this fascinating talk. So could you say a few words on the state of the art now in interdisciplinary and transdisciplinary modeling? I was not sure if you had coupled the models, especially for the coastal part. That interests me a lot. But also, as we go, Ben mentioned that you're in coastal solutions, into really transdisciplinary. For instance, for a hurricane, can we have also some socioeconomic data layers to see how much it will cost to rebuild, or things like that, human health, ocean health? Thank you.
Certainly. So this is something personally that I'm really interested in, but is also something, again, that's being widely worked on. And so something that's really great about these machine learning-based tools is that the majority of them were adopted from the computer science-based field. And so we already have one cross-disciplinary step here. But then some of the projects that I had highlighted here need that cross-disciplinary, it's really transdisciplinary, because no one person can be an expert in all of these things. But what these tools can help do, especially the XAI in building trust, can help break down some of those communication barriers for, say, someone who's maybe more used to the computer science language versus someone who's maybe working more on corals or sharks. And so I think that there's a lot of opportunity that's already being developed here in terms of using these tools to be integrating a lot of this data, things that can be really hard with traditional models, and help in communicating the uncertainty, those spreads in forecasts, the confidence, things that different sectors are looking for, different thresholds, say, that, again, can help with that communication barrier that we often see with interdisciplinary research.
Yeah, this question may be partly cross-disciplinary, maybe a little bit outside of your area of expertise, but you reminded me of something when you're talking about taking the native biology there based on the stress. And I know I've seen elsewhere that there's work being done here at this institution about finding, for example, resistant corals and trying to grow them. Do you know anything about where that stands and how successful we are at this point in trying to save the coral, or at least encouraging those that have already shown their own resistance?
Yeah.
Is that going on?
Yeah, so I'll reiterate, I'm a climate scientist using machine learning, and this is why I love interdisciplinary research, because it's exactly why we have these collaborative efforts. And so this is the Coral Project is something I had been working on with the NOAA Coral Reef Program, experts in exactly this heat stress and what sorts of temperatures, conditions these corals can be resistant to help with all different levels of decision makers, and what are the right stress thresholds to be predicting. This is something that I certainly couldn't have come up with on my own. And what are the right actions to be taking based on these certain predictions? When should action not be taken? There's tons of programs. I see people here in the audience working on exactly these types of problems. And so, yeah, I think it's an exciting space to be in.
I was just curious more about like logistically how you're incorporating AI into your research. Is it the tools that you were already using are like offering AI enhancements, or are you using some of the GPTs that some of us might be more familiar with and kind of like using that to using those tools to incorporate them into your research?
I would say that basically how you ask the question is how I incorporated the tools. So I first started building neural networks with the intention to make predictions within climate model data. Machine learning models are notoriously data hungry. We have a lot more climate model data. So I was building neural networks. I was trained to build neural networks with climate model data to understand connections, accuracy, predictability within the model data. And then eventually moving into other types of models like the random forest model with observational data. So it was very intentionally building simple models to explain them. I started doing machine learning around 2022. There's been an explosion in pretty much every way possible. In 2024, I got a laptop with a GPU on it. Wow. And so I started building neural networks that were then able to use 1 GPU, 2 GPUs, process way more climate model data. Now we're looking at using these huge supercomputers at iDisk, and plenty of other people are using these as well, in terms of actually running these emulators, generating simulations, things that require way more computational power. The 4 years I've been working on AI, it's incredible how widespread these tools and the advancements have become. And so it'll be interesting to see, in just a few years what happens. Maybe we have them on our phones. Who knows?
Thank you very much for your time.
Thank you.